So this video is going to cover the lecture that we had on 11-12, and I would like you to review section 7.1, which talks about alkyl halides. I will go over a couple of the basics, but you need to review nomenclature, and their uses. Alright, and then what I will do is in this video I'll talk about SN2 reactions, and then I'll make a follow-on video that should have been for the 14th about SN1 reactions and bring everything together. So some basics with regard to alkyl halides. When we're talking about alkyl halides, we're talking about the halogens. So this can be fluorine, chlorine, bromine, or iodine. We can have different types of alkyl halides. And what I mean by that is we can have primary, secondary, or tertiary alkyl halides. Now, if we were to look at an alkyl halide, the carbon attached to the halogen is the alpha carbon. And then, as we go out, we have the beta carbon. We can go further and say this is gamma, and so forth. So let's look at a primary, secondary, and tertiary alkyl halide. Let's define the alpha carbon. Okay. So here we have a primary alkyl halide. The alpha carbon is bonded to one carbon. Next we have a secondary alkyl halide. Here the alpha carbon is bonded to two carbons. And finally, we have a tertiary alkyl halide where the alpha carbon is bonded to three carbons. Alright, so now that we have those basics down, let's look at substitution reactions. Now we encountered a substitution reaction when we looked at the reaction of a terminal alkyne that's been deprotonated with a primary alkyl halide. So, the negative carbon attacks the alpha carbon, so the nucleophile attacks the alpha carbon, which has a partial negative. Because of the electronegative halogen. When this happens, the bromine leaves, and we form, so the bromine leaves, and we form a new carbon-carbon bond. And so I'll number just for bookkeeping. 1, 2, 3, 4. 1, 2, 3, 4. We formed a new CC bond. So this was an old reaction, but it is an example of a substitution reaction. Now, we need to figure out what is the mechanism of the substitution. And through experimental observation, we can either have an SN2 reaction or an SN1 reaction. Now the S equals substitution. The N stands for nucleophilic. And the number equals how many molecules are in the rate determining step. So the rate determining step of a reaction is the slow step. And if we were to define the rate of a reaction, the rate equals K, which is a rate constant, which is defined for a given temperature, times the concentration of the reactant. So let's just say we have A plus B goes to C plus D. And you would raise A or B to an exponent. And so this would define the rate of a reaction. Now, when we're looking at an SN2 reaction, again, so this is substitution. It's nucleophilic. And the 2 means that we have a bimolecular transition state. In the rate determining step. So if we were to take the reaction that we wrote before with the alkyne, well, let's just do a generic reaction. So say we have a nucleophile plus some type of substrate, and the LV means leaving group. Let's go to the next slide. Alright, so let's do this again. Nucleophile, substrate, the product would be a substitution where the leaving group left Now, for an SN2 reaction, both the nucleophile and the substrate are involved in the rate determining step. So, when we write the rate of this reaction, it would be K, some rate constant, times the concentration of the nucleophile times the concentration of the substrate. And these are raised to a power of 1, so really you don't have to write that in. So what this means is that the rate of the reaction depends on both the concentration of the nucleophile and the concentration of the substrate. And so when you change either the nature of these, the nucleophile or the substrate, or you change their concentrations, you are going to change the rate of the reaction. So now if I give you an example, say we have OH minus as a nucleophile and we have an alkyl halide. Now, this is going to go by SN2. You're going to have the nucleophile attack the alkyl halide. We have attack of the alpha carbon from the backside. In a concerted process, so happening at the same time as the nucleophile attacks, the leaving group leaves. You will get a transition state that is bimolecular. To draw the transition state, here's the alpha carbon, so you're forming a bond and you are breaking a bond. This is the transition state for an SN2 reaction. It's bimolecular. The final product would be this. We made an alcohol. Now a couple of things about this reaction that we need to note and remember. So again, with an SN2 reaction, we have backside attack. If the alpha carbon is chiral, then there is an inversion of configuration. And I'll show you what that means. So here we have a chiral alpha carbon. This alkyl halide is secondary. When we add OH minus, which is the nucleophile, the OH minus attacks from the backside, the Br leaves, and we have an inversion of configuration at the alpha carbon. This is only true when the alpha carbon is chiral. So let's summarize again for an SN2 reaction. We have backside attack, we have an inversion of configuration, if the alpha carbon is chiral, right? And also the transition state is bimolecular. Alright, we're going to add to this list as we look at this reaction more in depth. So I said with an SN2 reaction, the rate is the rate constant times the concentration of the nucleophile times the concentration of the substrate. So let's focus on the substrate. If we're looking at alkyl halides, okay, here I have a primary, followed by a secondary, followed by a tertiary alkyl halide. Because we have backside attack, there is less hindrance, less steric hindrance, for a primary alkyl halide. So what this means is that a primary alkyl halide is more reactive than a secondary, which is more reactive than a tertiary alkyl halide. So reactivity depends on the steric hindrance around the alpha carbon. If we were to take an SN2 reaction and just draw an energy diagram, here you have the reactants, which is the nucleophile plus the substrate. Here we have our transition state, which is bimolecular. And then we have our products. When you change the steric hindrance around the alpha carbon, you will have an effect on the energy of the transition state. So, if we draw an energy diagram, now, we know that, well, it's implied that there's little energy difference between a primary and secondary and tertiary alkyl halide. So let's say the red line is a primary alkyl halide. We have our reactants, our products. So the primary alkyl halide would be right there. Now, I just said there's little energy difference between a primary, secondary, and tertiary alkyl halide. So in blue would be my tertiary alkyl halide. Because there's more steric hindrance around that alpha carbon, the transition state is harder to achieve.